So let's take the first example to explain. We have 2, 3, 1, 2, 4, 3. So first we set I is 0, the j is 0, 1, 2, 3. The sum is 2, 5, 6, 8, but 8 is greater than or equal to 7. So we take the I is 3. So the length is j minus I plus 1, which is 4. The approach we use here just brute force, but the time limit is exceeded. We just do as directed in the question to find the sum for all the possible subarray, and then we update the minimal length. So the minimal length as when we get a better subarray that will fulfill the requirements, the sum is greater than or equal to target. Before we build algorithm, we need to first import math module. It is a built-in module in Python which will extend the list of mathematical functions. First, we initialize the minimal length assigned by math.inf. The math.inf is a constant returns a floating point positive infinity. Then we iterate the array from left to right using I, and we iterate from the current element to the end of vector using j. So we find the sum of elements from index I to j. If the sum is greater than the target, we just update the minimum of length. So the minimum of length, we compare it with the j minus I plus 1. Which one is smallest? We'll assign the value to the minimum length. Then we start the next ith iteration. Since we got the smallest subarray with sum greater than or equal to target, we just starting from the current index is okay. Let's try to turn the algorithm in Python. First, we need to declare a minimal length, which is the math.infinity, right? Then we can define a for loop. There are 3 for loop. For I in range, so I is iterate the whole nums array, and then we nest it inside the for j in range. J is from I to length of the lambs. Then inside it, we declare a sum of the subarray, which is start from 0. Then we can nest it a k nested in the j in range from I to j plus 1. Then the subarray is every time increment by the nums of k. And if the sum of subarray is greater than or equal to target, then the minimum of the length is get the update. We use the minimum function, compare the minimum length and j minus I plus 1, which is the current length. We compare it, which one is minimum. We have opportunity to assign the value to minimum length, and then we just return the minimum length, but only if the minimum length is not equal to math.inf. If it is math.inf, that means it don't change, right? If it don't change, that means we didn't find any number, any element can match the requirement. So we just return 0. Then we can write, yes, it is 2. Let's try to analyze its complexity. The time complexity is O of n cubed because for each element of an array, we try to find all of the subarrays starting from that index, which is O of n squared. So the time complexity to find the sum of each subarray is O of n. Thus, the total time complexity is O of n squared multiplied by n, which is O of n cubed. And the space complexity is just O of 1 because we don't use any extra space. In the first approach, you might notice that the sum is calculated for every subarray in O of n time. But in the second approach, we can optimize the brute force approach, which is accepted. We just storing the cumulative sum from the beginning, so we can easily find the sum in all of one time. We just use memorization technique. The memorization can be used to speed up program just by storing the result, which is expensive function call, right? So when the same inputs occur again, it will return the cached result. So after we have stored the cumulative sum in sums, we could easily find the sum of any subarray from I to j. The algorithm is similar to the first approach. The only difference is in the way of how do we finding the sum of subarray. We just create a new array, which is press sum to hold the value. First we initialize each the element is full of all of 0. Then we iterate over the press sum array just by adding them one by one to get a cumulative sum. So the sum of subarray from I to j is calculated as press sum at j plus 1 minus press sum at I. So it is the element from the I to j plus 1. So let's try to turn the algorithm in Python. First, we need to declare the press sum, which is fill in with element 0, which is array, and the current sum is 0. And then we need to calculate the current sum for num in nums, the element in nums. The current sum is increment, every time increment sum, and the per sum will dot append, every time append the current sum into the per sum, and then we get the per sum right, so we can declare a minimum length. The minimum length is first initialized to the mass dot infinity, and we can start run the to for loop for I in range. The maximum is the length of the length, and for j in range from I to length of length, which is the last one, and then we can run this nested for loop in the per sum. If the per sum j plus 1 minus per sum at I. So this is how we calculate the sum of subarray, which when it is greater than the target, then we can update our minimal length. The minimal length, we use a minimal function to compare with the minimal length, the current minimal length, and the length, which is j minus I plus 1, the current length, and then we can just return the minimum length. Only if the minimum length is not equal to max dot infinity, because if it is equal to max dot infinity, that means they didn't change. They didn't change means there's no situation, no elements match the requirement. So that means there's no situation exists, no case exists, we just return 0 in that case. So let's try, it will print out 2. That is how it works. Let's analyze its complexity. The time complexity is O of n squared, because the time complexity to find all of the subarrays is O of n squared, and the sum of the subarray is calculated in O of 1 time. Thus the total time complexity is O of n squared multiplied by 1, which is also O of n squared. And the space complexity is O of n extra space, because we use additional O of n space for the subarray, which is more than the approach 1. We could further improve the second approach just by using binary search. Notice that we're starting with an index I in O of n time to find the sum of subarray who is greater than target. But if we're using binary search, we could reduce the operator time to O of log n time. Notice that in the second approach, we search the subarray starting with index I until we find the sum of subarray that is greater than target. So how could we calculate the sum of the subarray, which is sums at j minus sums at I plus nums at I? So instead of iterating linearly one by one to find the sum, we use binary search to find the index, who is not lower than the target. We will record its lengths of them, and then we compare with the rest of the other lengths. Then we can get the minimal length. Which one is the minimal length? Let's build the algorithm. We will using an additional array to store prefix sum just by creating an array to hold the sum's values. Its size is n plus 1, and the first element is sums at 0, which is 0, and the rest of the element is sums at I minus 1 plus the nums at I minus 1. Let's try to build algorithm in Python. First, we declare a variable result, which is the math.infinity. It is the biggest number integer in the Python. And then we set a new array sums, which is all the element initialized to 0, and then multiplied by the length of lambs plus 1, because the first element is 0. And then we can start a first for loop for I in range from 1 to length of sums. So this for loop is to write the sum into sums array. Sums at I every time get updated by the sums at I minus 1 plus nums at I minus 1. So then we can set another loop in the sums, because sums already read the element inside it. We from 1 to the length of the sums. So we have in order to use binary search, we have low and high. So low is I, every time start from I, and the high is always the length of the sums minus 1. And this is how we start, while the low should always less than or equal to high, and the middle is low plus high flow division by 2. So if the sum at middle minus sums at I minus 1 is less than target, then the low should move to more higher. It's minus plus 1, because it is too low, we need to move it to higher. So else means it is greater than or equal to target. That means the result, that's what we want. So we should update the result by the minimum function with the existing result and minus I plus 1, so which is the current length of it. So the higher is get the move to the lower by the minus 1. Then we are done. We just return the result. Only if the result is not equal to infinity. If it is equal to infinity, that means it didn't change. So no element meet the requirement. Then that time we just return 0. Yeah, that is true. Let's analyze its complexity. The time complexity is O of n multiplied log n, because for each element in the sums of array, we're using binary search to find in the subarray, starting from that index and having the sum is greater than target. Hence, the time requirement is O of n for iteration over the sums array. And when we're using binary search, it costs O of log n time for finding the subarray for each index. Therefore, the total time complexity is O of n multiplied log n time, and about the space complexity is O of n, because we use additional O of n space for new array sums. Until now, we have kept the starting index of the subarray fixed, and trying to find the last position. Instead, in the fourth approach, we could move the starting index of the current subarray as long as we know that there is no better could be done with this index as the starting index. We could keep two pointers, one for the start and the other for the end of the current subarray, and make the optimal move. So as we keep the summer is greater than target, and as well as maintain the lowest size as possible. So let's try to build the algorithm first. We initialize the left pointer to 0 and the sum to 0. Then we iterate over the names and we add names at I to sum. Where the sum is greater than or equal to target, then we update the ends. The ends is the minimal function of the existing ends and I plus 1 minus left pointer. So which one is the smallest, we'll have opportunity to write the value into the ends variable. Well, the I plus 1 minus left pointer is the size of the current subarray. It means that the first index can be safely incremented since the minimal subarray starting with the index with sum is greater than or equal to target has been already achieved. Then we just subtract the names at left from the sum and increment the left pointer. Let's try to build the algorithm in Python. First, we set n is the length of the lambs, and we set ends to hold the which one is the minimal length. Would first initialize it to the method infinity, and the left pointer is start from the left, and the sum is initialized to 0 first, and we set a right pointer for I in range n. So I is our right pointer, it will run faster than the left pointer. The sum is every time add by the names at I, so it is the sum. And where the sum is greater than or equal to target, it will meet my requirement. If it meet our requirement, I need to update our ends, which is the minimum of the ends compared with the current is I plus 1 minus left is current length of the sum, and the sum is after finished, because it is greater than the target, we can make it the shorter one is sum is minus the names at left, and then we increment the left pointer every time we move to the right, and after we finish we just return the ends. Only if the ends is not equal to mass dot infinity. So if it is equal to infinity, that means that shows no change. If that don't change, we just return the 0. Yeah, it's 2. That is how it works. Let's analyze the complexity. The time complexity is just OFN because we just use single iteration of OFN. Each element can be visited almost twice. Once is by the right pointer I, and the other is almost once by the left pointer. And about the space complexity, just O of 1 extra space, because it is only constant space required for the variable left, sum, and ends.